Good evening and welcome to the Marion Minor Cook Athenaeum. My name is Sophia Cravazzi and I'm one of your Ath Fellows this year. In the 20th century, technologies such as aircraft, the telephone, and the internet changed our world, to the point where life today is inconceivable without them. Our speaker this evening, Dr. Susan Hockfield, former president of MIT and world-renowned neuroscientist, argues that in the 21st century, radical new convergence technologies will play a similar role to reshape every facet of our world. Living machines like virus-built batteries, big data-designed food crops, mind-reading bionic limbs, and countless other inventions are taking over. With an eye towards how they will affect various industries, from energy to manufacturing to healthcare to agriculture, Hockfield provides a first glance into the shape of the world to come. She aims to show us how we are on the cusp of a new convergence where discoveries in biology are intersecting with engineering to produce an array of almost inconceivable next-generation technologies. These advancements highlight the promise of the technological revolution of the 21st century, which might just enable us to overcome our greatest humanitarian, medical, and environmental challenges. A neuroscientist by training, Hockfield was the first woman to lead MIT and is the author of The Age of Living Machines, which speaks to the technological biological revolution known as convergence. Hockfield's career has spanned some of America's most prestigious schools. Throughout her time at Yale, she was a professor of neurobiology, then dean of the Graduate School of Arts and Sciences, and then their provost. She then moved to MIT, where she served as the school's 16th president. She was the first woman and the first scientist to lead the institute. Hockfield has also held the Marie Curie Visiting Professorship at Harvard University's John F. Kennedy School of Government. She has served as a U.S. Science Envoy to Turkey with the U.S. Department of State, and served as the inaugural co-chair of the White House-led Advanced Manufacturing Partnership, a task force of government, industry, and academic leaders. Currently, she is a member of MIT's Koch Institute for Integrative Cancer Research and professor of neuroscience at MIT. Now, regardless of how life-changing technology is, I must remind you that audio and visual recording is strictly prohibited, and you must now silence and put away your electronic devices. Dr. Hockfield's Athenaeum presentation is co-sponsored by the President's Leadership Fund. And now, without further ado, please join me in welcoming Dr. Hockfield to the Athenaeum.
I did not get a pointer. Do you have a pointer for me? Or a slide advancer pointer? It'll be coming up. So thank you, Sophie. And I want to thank you all for coming this evening. I've had a fascinating day here. I have to say, I'm a bit of a campus junkie. And in my former life as a scientist, I wasn't that curious about campuses, universities, how they came to be. But I had the very good fortune that my life took a turn that opened up another universe to me, and I've become, quite a student of campuses. And I have to tell you, yours is very special. I've loved being here. A lot of interesting things going on here and fabulously interesting students. I'm going to be talking tonight about the convergence of biology with engineering, and it's the story that I tell in my book, The Age of Living Machines. And I hardly have to give this talk here because most of the students who I've talked to, thank you very much, tell me they're majoring in, I wouldn't say X and Y, I would say B and M, or just these very, very disparate disciplines. And so it's exciting to me that so many of you understand that bringing different disciplines together will give you a new perspective on the world as it is, and more importantly, a new perspective on the world as it will be. So it's really, really exciting. So I have had the amazing privilege of leading one of the world's great universities. As you all know, MIT is a little bit more technologically inclined than most. And I have to make one correction. I was the first woman to be president of MIT. I was the first life scientist. There was a physicist before me who had been president, and that, frankly, was pretty much in line with MIT. Being the first biologist president was more disruptive, frankly, than being the first woman president. But it worked out anyway. So as president, I had an extraordinary perspective across the frontier of discovery, innovation, technology development. And what I saw from that perspective surprised me and gave me a very optimistic view of the world ahead of us. It's about how biology and engineering are coming together, and I'm going to tell you that story. But it really is, there are great possibilities for creating the technologies that we will need. And it's important for me to actually talk about that because while I feel that there's great optimism, there are a lot of reasons that we perhaps might not be so optimistic. So let's just remember where we are today. We have roughly 7.5 billion people on the planet. It is predicted by very reliable sources that we will have over 9.5 billion, close to 10 billion by 2050. You know, that's pretty daunting if you think about several things that we're already not doing well enough at. And I have called out a few of them here, and the list is much longer. And I'm happy to discuss any of the pending problems with a large population afterward in the Q&A. Obviously, healthcare access, accuracy, and cost. In the United States, we currently are spending upwards of 18% of GDP on healthcare, and you know, we have some miraculous new ways of treating disease, but frankly, the access is poor, the cost is high, it is unsustainable. Energy, one of my favorite areas of interest. We are already not meeting the energy demands of today using our current energy technologies with very serious implications for the future of the planet. It is predicted that this population, 9.7 billion, the energy demands will be double what they are today. We've got to get a whole lot better in providing energy to meet our needs. And water and food sufficiency and security, what is it, every month, every 2 months, we hear about some place that has a water crisis? Pure water, sufficient pure water is a problem already today, and it's going to be an even greater problem later. There are people who predict that simply water provision is going to be the cause of enormous political disruption going forward. So, sounds pretty awful. I'm not sure this is going to be much solace to anyone, but we have been here before. Some of you may have heard of the Reverend Thomas Robert Malthus, perhaps. Malthus wrote a treatise on population in 1798, an essay on the principle of population, and he made the observation that perhaps wasn't surprising even at the time. But the observation was that if you look at the rate of population growth at the time, it was greater than the rate of growth in agricultural productivity. Not a happy imbalance. And he did a beautiful demographic study of Western Europe and Britain, and he concluded that this had happened before. Episodically, there are times when the population growth outpaces the growth in agricultural productivity. And he wrote his essay as a warning. He said, we've been here before, and it always ends in tears. What happens when population growth outpaces agricultural productivity? War, pestilence, famine, terrible things happen that reduce the population back to a level that the resources can provide for. So he wrote this as a kind of a warning. Watch out, this is going to happen again. And actually, any of you who have read this essay will remember that he had some, let's just say, shall we say, socially unacceptable ways of controlling population. So it ended up, Malthus was wrong. In 1798, he was wrong because there were new technologies for agricultural, for farming that he didn't know about. British farmers had started going from 3-field to 4-field crop rotation. That made their fields more productive. And there was a fabulous new technology. Now, I don't know when in your curriculum in grade school you studied those seafaring pioneers who were sailing the world looking for gold, jewels, tobacco, all those exciting things. Well, they were doing that, but as they were sailing around the world, they also came upon islands inhabited only by birds, and only by birds for centuries. Those islands, you couldn't actually get to the land because they were piles of bird poop, guano. And guano is an extraordinarily effective fertilizer. So there was an incredibly important trade in guano from these islands, many of them off the northwestern coast of South America, that created a burst in agricultural productivity in Britain. Actually, population grew faster even than Malthus had predicted. People were fed. And if you want to put a happy story on that, there were enough people to populate the positions that emerged out of the Industrial Revolution. So how did we get out of that Malthusian dilemma? By innovation. How are we going to get out of today's Malthusian dilemma? I think also by innovation. So I'm going to tell you the story of what I think is going to be the technology story of the 21st century. And as president at MIT, my responsibility was to chart a course of, so everyone blames the president for everything that goes wrong, right? Today, next week, next month, last month. And so it is the president's responsibility to just kind of say, yep, bad things happened. But the president's real responsibility is to position your institution for the long term. Colleges and universities are among the most long-lasting institutions in world history. And that happens because universities position themselves so that 25 or 50 years from now, they're going to be where the future is happening. So my responsibility as MIT's president was to think, that far out in the future. I mean, come on, I get to the office, I open all the drawers looking for the crystal ball. The one I brought with me from Yale was a little foggy after 5 years. So, I mean, I figured out better than a crystal ball. If I could figure out the future we're living in today and how we got to this future, maybe that would give me a clue to figuring out the future we'd be living in tomorrow. So, what technologies have most profoundly transformed our lives in the 20th century? I would simply ask, how many of you have one of these? Right? Digital technologies have transformed our lives in ways that are hardly imaginable, certainly would not have been imaginable in, let's say, 1970 or 1975. Where did those technologies come from? So where they came from was an earlier convergence, a convergence of physics with engineering that produced these wonders and much, much more. What technologies are now coming out? Biology with engineering will do the same thing for the 21st century. So let me tell you the story. Actually, I don't need to go over there, I can use this. So this shows you some of my heroes of Convergence 1.0, the convergence of physics with engineering. So on the left is Michael Faraday. Many of you may know of him. He did brilliant behavioral studies of electromagnetism. He had no idea what was giving rise to these forces, but he studied them in extraordinarily brilliant ways. And frankly, no one knew what was giving rise to these forces until people like J.J. Thomson, illustrated on this side, discovered the electron in 1897. So it is the movement of electrons, the electronic forces that give rise to the electromagnetic forces that Faraday was studying. And with J.J. Thomson and his colleagues' discovery of the components of the atom, there was a parts list of biology. Engineers picked up those parts and invented the technologies of what became the electronics industry. There wasn't an electronics industry in 1900, but there sure was an electronics industry by 1920. The electronics industry then gave rise to its successors, the computer and information industry. So the way I look at the 20th century's technology story as Convergence 1.0, the convergence of physics with engineering. Now, I probably don't need to remind people in this room, but let me just tell you that neither Faraday nor Thomson was doing the work they were doing so that you and I could have iPhones. They were doing their work because they were simply curious about the world around them. They wanted to understand how things worked. Now, I understand that, having participated in this world of discovery, but people always forget that fundamental discovery lays at the foundation of new technologies. And here's an example. This may be apocryphal. So on the left is William Gladstone, Chancellor of the Exchequer, essentially the Secretary of the Treasury in Britain, and he is reputed to have asked Faraday, why are you wasting time and money doing these kinds of experiments you're doing? What's the purpose? What's it good for? And Faraday is reported to have replied, I have no idea what it's going to be good for, but someday you will tax it. And indeed, there's a lot of tax going into our country's coffers by every electronic marvel that we purchase. So the electronics industry got started. It was moving along with, reasonable rapidity, but nothing accelerates technology more profoundly. The best catalyst for technology development, unfortunately, is war. So So World War II is called the Physicist War, and it's called the Physicist War because of the technology that was developed in the face of the threat by Germany. In the United States, this man, Vannevar Bush, was the architect of the technology development, not just in the United States, but also among the Allies, that produced the war-winning technologies, include radar, sonar, nuclear weapons and nuclear power. The foundations of computing were actually established during this, an amazing technology effort. Now, as the war was drawing to a close, the president, FDR, Franklin Delano Roosevelt, asked Bush what he would suggest for the nation after the war. Now, wars are not happy situations. They may develop technology, but there are a lot of other things that are not so happy. And one of the unhappy things that a war presents is bankruptcy. So every nation that's involved in war spends every dime they have and every dime they can borrow to defend themselves against the enemy. So nations emerge out of war in a state of bankruptcy, and the response to that is to stop spending money. So after wars, most countries fall into economic depressions. And Bush wrote a treatise called Science, the Endless Frontier, in which he poses to FDR a very different strategy. Rather than pulling back on spending, we should double down on the kind of investments in technology that succeeded in winning the war. And what he says in his report back to FDR is the lessons learned in the wartime application of science can be profitably applied in peace. Some of you may have read some of Science, the Endless Frontier. It is, to my mind, even today, astonishing. He lays out a blueprint for the second half of the 20th century in America. He describes the GI Bill. He describes mortgages for GI. There are people who are coming back from the war. They're not trained for any kind of new industry. They don't have the money to buy houses. They need to live someplace. Really a problem. So he talks about community colleges. Most importantly for my discussion today is he talks about continuing these massive investments in the development of technology. And he says, I know it seems like a lot of money, but you know what? What's going to come of that is an entirely new economy, new discoveries, new industries, and economic growth. He was right, eventually, but FDR died. And FDR's successors were, let's just say, less enthusiastic about spending and spending and spending. I'm reading a new biography of Eisenhower, and indeed, one of Eisenhower's triumphs when he was president, post-war, was to come up with balanced budgets. And Bush had said, no, we don't want balanced budgets yet. Later, because what we need to do is invest in technology. So some of that investment was happening, but not enough. Until there was a surprise. The Russians got into space first. And this caused the United States to kind of rethink our priorities in terms of investments, and President Kennedy initiated the race to the moon. Now, he announced it in 1961, absolutely lunacy, because we didn't have any of the technologies in hand that would allow us to put a man on the moon and, let's just say, bring him back. Half that journey is probably easier than the round trip. So he said any number of speeches, made many speeches about it, and I have chosen this particular quotation from a speech he gave at Rice University. And this has now become very popular this year as we celebrate the 50th anniversary of men walking on the moon. He says, we choose to go to the moon in this decade and do the other things, not because they're easy, but because they're hard, and because that goal will serve to organize and measure the best of our energies and skills. He set out a national ambition. And for those of you in the room, there aren't many who were actually alive during this time, it was a time of national turmoil. There were race riots, our cities were burning, incredibly difficult things were happening, and yet in the midst of all of this turmoil, Kennedy said, together as a nation, we're going to go to the moon and back. So this kind of national ambition, I have become an incredible proponent of shared ambition. And one of the reasons I'm an incredible proponent of it is because this national ambition, of course, affected the thousands of people who were working on the Apollo project, but it infected the nation. So at the time, I was in second grade. People asked me how I had the life I had, how I became a scientist and beyond. I have simply said, I grew up under the shadow of Sputnik. Here I am with my three sisters. I'm second in my family. And my mother bless her heart, was a saver. And among the things she saved were essays that my sisters and I wrote when we were in school. And she shared this one with me. I'm embarrassed to share it with you, but I will. This is an illustrated essay that I wrote when I was in 2nd grade. And I have, some of you can actually see my bad spelling and bad grammar. I've cleaned it up over on the right just so you get a sense of what I was talking about. It's hard to gather that if you read the original. By the way, I clearly was not much of an artist. One of my sisters is a very good artist. I was not much of a writer. One of my sisters is a very good writer. And I didn't know much about spelling or grammar. I was slow to learn those things too. And penmanship, let's just say, was never my strong suit. In any case, I talk about something, I'm writing it as if it were someone else's biography. I didn't know at the time that it was going to be my autobiography. But science is a very interesting subject. You can learn a lot from it, and maybe you'll want to be a scientist, and you will figure out things. Maybe you'll figure out how to go to the moon. So this reflects this idea of a national ambition. That 2nd graders all over the country were animated around the possibility of science and technology to accomplish something really important. And by the way, it would be fun. And I can assure you it has been a lot of fun being a scientist. So back to the main story, which is if we look at the products of Convergence 1.0, of the convergence of physics with engineering, they animate our world, improve our health, provide opportunities for us that we never imagined possible. So while this Convergence 1.0 was going on, where was biology? Biology was nowhere. Biology was not nowhere, but it was a descriptive science because we didn't know, we were where Faraday was. We didn't know what the component parts were. And that began to change with 2 revolutions. The first was a revolution in molecular biology. The second was genomics. And let me just tell you briefly about them. Molecular biology changed our understanding of living things. When I was in college, our biology department taught separately microbiology, botany, animal behavior, anatomy. They were all separate. There was, even though, trust me, I went to college well after 1953, but there was no real conveying in our education that molecular biology provided a unifying idea, a unifying structure for all of biology. It has allowed us to identify diseases for genes and develop therapies against them. Bob Weinberg discovered a gene called HER2, which is an oncogene, one of the first oncogenes, in the mid-1980s. By the end of the 1990s, Genentech was marketing a drug called Herceptin. This is a drug for what was previously a death sentence kind of breast cancer. Just one example of the array of new medicines that have come out of molecular biology. I'm showing you some of the leaders of that movement, Francis Crick, Jim Watson, Rosalind Franklin, Maurice Wilkins. There were dozens of people working on this new science, and interestingly, many of them were physicists. So one gene at a time out of molecular biology, very important. But molecular biology didn't really get its mojo without genomics. So the Genomics Revolution, the idea that you can sequence lots and lots of genes and compare hundreds or thousands of genes with one another, allow us to approach problems of biology, problems of medicine in an entirely new way. Talk about technology development. What this slide shows in the red line below is the rapidity of the reduction in the cost of sequencing a human genome. Not that I necessarily have to compete with my physicist friends. However, above it, I show Moore's law, which also has been an astonishingly rapid development. That is, how many transistors can fit on a chip. Right now, we're over 18 billion. Amazing. From the earliest chips, which only had 40 million. But if you think about the cost of sequencing a human genome, if you're cheap, you can do more of them. So it's very important to get the cost down. The first human genome cost somewhere between $100 and $150 million. Took about 15 years. Today, you can get your genome sequenced for well less than $1,000, depending on how precise you want the information. And my colleagues across the street from the Koch Institute, where I sit at the Devote Institute, tell me they can sequence a human genome in 6 minutes, allowing us to gain all kinds of genetic information, to look for genes for complex diseases, to look for things that, and when an epidemic comes through, some people get it, some people don't. You want to know what the genome of the resistant population is so you can help design ways for people to not get the disease. So genomics molecular biology gave us a parts list of the biological world. Now, when I arrived at MIT, it was important that I learn as much as I could, being an alien from another school and a biologist. And among the people I met with at the very outset was the dean of the School of Engineering, Dean Tom Magnanti, a great guy. And when I sat down with him to learn what I needed to know about MIT, he first said something very important. He said, remember, the School of Engineering at MIT is our largest school and our most important school. I said, yes, sir. That was not so surprising. But the second thing he said was incredibly surprising. He said, this is in 2004, a third of the almost 400 faculty in MIT School of Engineering were using biological parts in their work. So I somewhat cheekily said, oh, yeah, biomedical engineering. And he said, yeah, sure, there's biomedical engineering. But they're using biological parts for everything, way beyond biomedicine. So that's where this idea began. If you have a parts list, engineers will pick up those parts and invent new things. So I'm going to give you 3 examples of what I mean by convergence 2.0, this convergence of biology with engineering. And I'm choosing examples that address some of the problems that I listed on the slide of the Malthusian dilemma. One example from medicine, one from energy, one from water. So the medicine example highlights work of my colleague Sangeeta Bhatia. Sangeeta is an MD, PhD. She's a nanotechnologist. Now, I'm going to give you kind of, just as an example, I could choose any disease, but let me choose cancer. So if you want to not have cancer or not die of cancer, the first best thing, don't get it. So you don't get it by getting the vaccines that prevent viral infections that we know can lead to cancer. You don't get it by stopping smoking. You don't get it by, unfortunately, I'm so bad at this, you wear sunscreen when you go out in the sun. I should be doing that more often. And you know, prevention is really great. There has been a 50% decline in death from lung cancer since 1990, mostly due to smoking cessation. However, even if we all did everything we could do, people would still get cancer, so the next best thing is early diagnosis. Cancer is a disease that starts as a single cell. One cell becomes 2, becomes 4, becomes 8. Eventually, the cell mass is large enough that pieces of it depart from the original site and will metastasize, move to another site. At that point, you know, when a cell mass is large, when parts of it have metastasized someplace else, it is very hard to treat. And truth be told, right now, we have some good diagnostic techniques. Most of them are pretty late. So Sangeeta has started a company called Glimpse Bio, which is designed to build what she calls synthetic biomarkers using nanoparticles. So here's the scheme. She starts with a nanoparticle, and she decorates it with little short stretches of proteins. Now, one of the amazing things about the biological world is that every cell does its own specific task by making specific proteins. So your liver cells don't look like your skin cells, don't look like your eyelid cells, because they're different kinds of cells that are running their own program. Cancer cells do what they do because they make their own specific proteins to do their job. So the reason that if a liver tumor will kind of grow in the liver where your liver cells are behaving themselves and doing what they're supposed to do and liver cancer doesn't, and the reason that a liver cell can get out of the liver and move someplace else is they make specific, basically molecular scissors. They're called enzymes that cut proteins, and they cut proteins at very specific sites. So what Sangeeta has done is these little protein tethers, in it she's designed the site that a cancer enzyme will cut. This little Pac-Man represents a cancer enzyme. So if you get these nanoparticles by injection and you don't have cancer, they stay intact, and you end up getting rid of them the way your body gets rid of all kinds of waste products. If you do have cancer, this little Pac-Man will clip off all of these little tethers and produce these little short little blue rings. And these blue rings, Sangeeta is actually designed to be very, very small. They're so small that once they're cut off, will find their way back into the bloodstream. And then even more importantly, once in the bloodstream, they are so small that the kidney will filter them into the urine while leaving everything else in the blood. So normally, the urine has very, very little protein, which means that if these little protein pieces are present in the urine, you can detect them. So she's developed a method to do a urine diagnostic. And right now in experimental animals, she can detect tumors that are 1/10 the size of best-in-class early cancer detection techniques. That would be a fantastic improvement. And you know, people say, well, can you actually detect something in a urine? And I probably don't need to remind this audience that there is a very inexpensive, very accurate, over-the-counter urine detection technology out there. They're called pregnancy kits. So the technology has already been you know, in use, and St. Kitty is piggybacking on that. They are in clinical trials now with this, and it could really change the game for cancer. If we can detect cancers when they're 1/10 the size of current techniques, we would be able to cure more cancers. Second example is energy. I've spent a lot of time at the table tonight and all during the day talking about energy and how we're going to get to a cleaner energy future, a less carbon-intensive energy future. Now, I can get kind of excited about solar, and I can get kind of excited about wind, but the rate-limiting technology for almost all alternative energy technologies is not solar cells or wind turbines. It's energy storage. So we need better batteries. Current lithium-ion batteries that we're using in any number of things are not sustainable. Manufacturing lithium-ion batteries takes enormous energy. They're built at incredibly high heat, and there are plenty of toxic byproducts. So we have to get better at storing energy. Angie Belcher, another colleague of mine at the Koch Institute, is holding an abalone shell in her hands, and the abalone shell is filled with coin cell batteries. Little coin cell batteries look like the plain old batteries that you use to replace your television monitor with, but actually those are filled with a biology-based battery. So she's holding the abalone. It's been her inspiration. She went to school at UC Santa Barbara. She used to walk the beach. I like walking the beach. I do it with less purpose than Angie. So she walked the beach because she was fascinated by abalone, an abalone shell. And I forgot to bring mine with me, because I usually have one to hold up because they are just so beautiful. She says they're lightweight, they are strong, but even more amazingly, the abalone, a sea snail, makes these shells out of components in the ocean in which they live in. The shells are brilliant technology for what an abalone needs. And when the abalone dies, the shell disintegrates into its component parts for the next abalone to build its shell. And so Angie says, if abalone can build the technology they need without contaminating our world, why can't we do that? And that's Angie's purpose. So what she has done is used what is a standard lab strain, benign strain of virus called M13. Now, and she has modified these viruses to build batteries. Simple. Let's just back up a little bit. So you know, viruses are not designed to bind to lithium or magnesium or cobalt or single-walled carbon nanotubes, which is what Angie uses to make her batteries. Viruses are designed to bind the respiratory lining of your lung, right, or of your nose and give you a cold. That's what viruses do. They bind organic material. So Angie's first challenge was to determine whether she could get M13 to bind inorganic materials like metals. And she has done that, partly by evolving batteries very, very quickly, growing them on the components she wants them to bind to, and partly by genetic engineering. What she has done is develop strains of virus that gather the components, organize the components of anodes, different strains that organize the components of cathodes. She packages them again in these coin cell batteries, and they work. Actually, they work really well. Her virus-enabled batteries have the same charge density and the ability to discharge and recharge of state-of-the-art lithium-ion batteries. But the best news is that her batteries are made on the lab bench at room temperature without toxic byproducts. That would be a great advance. I came back from one of these talks. Someone had asked me a question I couldn't answer, and I saw Angie in the corridor. I said, Angie, tell me about this. And she looked a little embarrassed, and she said, oh, we're not using lithium anymore, and we're not using cobalt. So she's now using cobalt and lithium-free batteries, again, to create the battery of the future. This would be a game changer. And happily, at MIT, I had a chance to see probably 24 new battery technologies that would be far better than lithium-ion, and we really have to double down on getting those batteries into the market. Third example is not from MIT. I can't be all MIT all the time. And this is about water. And I cannot begin to describe with sufficient hysteria how important water purification is. We've been using the same methods for water purification for, 3,000 years. Filtration and distillation. These are slow, expensive, and laborious. So this is a story that goes back to basic biology. Coming out of the lab of Peter Agre. Peter Agre is a hematologist at Johns Hopkins University, and he decided as a hematologist that he wanted to study a blood protein called the Rh protein. It used to be that Rh protein caused a problem that mothers whose fetuses did not match their Rh type could raise an immune response to the baby's red blood cells and either damage the developing baby or actually kill it. We know how to mitigate it, but we didn't know what the Rh protein was. And so Peter resolved he was going to find it, purified lots of red blood cells, took the proteins out of the red blood cell membranes, and purified them, until he had a single band. He was sure that he had gotten the Rh protein. He tested it, and he did not. He had something wrong. And that's happened to me. I've done protein purifications and gotten the wrong protein, and what I do is just go back to the bench and try again. And Peter did do several rounds, but there was something about this protein that he kept getting that fascinated him. Couldn't figure out what it was. And a friend of his suggested that maybe he had found the water pore. Now, let me tell you something about how cells work. Cells, each of our cells is like a balloon that is filled with the components that a cell needs to do its job. But things have to get in and out of this balloon in order for the cell to live and produce whatever products it needs to produce. And what happens is the surface of this balloon is punctured by pores. Basically, it looks like a barrel without a top or a bottom. And when it was first determined that cells had these channels, the physiologists went crazy, and they identified a sodium channel and a chloride channel and a potassium channel and all these channels, but they couldn't find a water channel. No water channel. And so the assumption was that there isn't a water channel. Somehow water goes across the membrane by diffusion. This colleague of Peter's suggested that maybe he had found the water channel, and Peter said, wait a minute, there isn't a water channel. Are you suggesting that I turned my work to working on a protein that no one believes exists? And somehow, guess what? He had, by accident, purified the water channel. He called it aquaporin, beautiful, water channel. And what this shows is a cross-section of a water channel. These little objects here represent the membrane, basically the balloon surface. And this is a cross-section of the aquaporin barrel that sits in a membrane. And these are little water molecules that are going through. And Peter did incredibly beautiful work on this and described the biophysics of how the water passes and why the water channel passes only water and nothing else. Absolutely brilliant work. And he won the Nobel Prize in Chemistry for it, well-deserved. And aquaporin is in every cell, in every living thing. Not an insignificant finding. But here's where things get just, I wish I could imagine these things happening before someone tells me that they happened. A biophysicist who was then at Illinois, Peter Holm-Jensen, read the paper of Peter Agre's that actually described this structure. And he thought, wow, that is so amazing. What a beautiful structure. Huh. If that aquaporin molecule can purify water for cells, maybe it can purify water for us. So he left his faculty position and started a company. It's called Aquaporin AS, and is now building water filters using aquaporin as the filter device that purifies water. This shows a little, this would be a vesicle. So these are little vesicles that are studded with these aquaporin channels. This shows it in cross-section. So this is contaminated water on top. They're little red, nasty things. And these water molecules go into this sphere and out it, and down here is pure water. This is one of the filters that Aquaporin AS is making. They are now being used in homes in Asia. They have a collaboration with a Chinese, a Singaporean company. And their ambition is to scale up these filters to do the really heavy-duty tasks that we need for water filtration, like desalinization. I hope it's going to work. It's fantastic. But Peter Holm-Jensen, not Peter Agre, who told me other very interesting things, but Peter Holm-Jensen said to me when I visited the company, he said, You know, I could bust my brain trying to figure out how to build a better water filter, but why don't we just use nature's genius? And boy, I wanted to call my book Nature's Genius because it really does capture the point. Nature knows how to do all kinds of things better than we, and why don't we just figure out how nature does it and then import those technologies? Anyway, so those are 3 examples. Now, all of these examples, excuse me, require multiple disciplines. Again, I celebrate all of you who are studying multiple disciplines. It's very, very hard to make cross-disciplinary work succeed. I mean, how do you implement it? There is the innovator's dilemma, as described by, very sadly, the late Clay Christensen, which is that if your structure is working pretty darn well, why would you mess it up? So right now, having an engineering school separate from a school of science, engineering departments separate from biology department, why would you change? Well, you change if there's an opportunity, but it's very hard. And actually, if you can structure some kind of crosstalk, and it's why I love that you all are studying 2 different disciplines, because if you're only studying one discipline, you only know that language. And I can tell you, when you try and put engineers and biologists together who aren't prepared, they can't communicate with one another very well. They have different approaches. Engineers characterize problems very differently from how biologists characterize problems. And there are any number of institutional and interinstitutional barriers to actually working together, not to mention our funding agencies. Excuse me one second. So, the National Institutes of Health funds biology and biomedical science. Can't get an engineering project through. National Science Foundation, computer science, engineering, Department of Energy funds physics. Very, very hard to get funding for any activity that crosses disciplines. So we've managed to do this at MIT, and I want to just give you one example of how it's worked. So this is the Koch Institute for Integrative Cancer Research, where my office is. It is a mashup of biologists and engineers with the shared ambition, you see the theme emerging again, of accelerating progress against cancer. This was engineered, a lot of social engineering and physical engineering to make it work. And let me tell you about 4 layers of collaboration that we've built into it. The first is the footprint. It was designed so that biologists and engineers have to cohabitate. This was the original plan, where biologists would be on one side of a floor, of each floor, and engineers on the other. But now, with faculty turnover, people like this. And this would now look more chimeric. There would be engineering labs here and biology labs here, so it's become even more integrated. The building is 6 stories, 1 stairwell, 1 set of elevators, 1 cafe, 1 set of restrooms. No matter where you go, you're going to run into someone who's not from your clan. And it's been very productive that way. We've embedded it in an ecosystem where we have faculty in the Koch Institute. Their faculty appointments are in standard departments. That would have taken me about 400 years to change. But we can move their research lab someplace where they share. And it's embedded in a location on campus where they can interact with faculty from other disciplines. MIT does not have a medical school or a hospital. It's kind of hard to work on a clinical problem where you really want to have applications without it. So we developed something called the Bridge Project that connects the Koch Institute with the Mass General Hospital, Dana-Farber, and Brigham and Women's hospitals in order to bring clinical expertise into the mix, and that has been really critical. And then the fourth advantage that we have, and I don't know, happily it was there and I didn't have to build it, which is the Kendall Square Innovation District. So this shows MIT. This is the Koch Institute here. And this is a subset of the array of biotech, biopharma, VC companies around us. My colleague Phil Sharp, who shares my office suite, says technology travels on 2 feet. And there's a lot of advantage in being very close to people who can help you bring an idea to market. The Koch Institute, since its founding in 2007, I think we count somewhere north of 80 companies that have spun out, with over 30 of them already in clinical trials. So we have proved our concept, which is If we put this together, we can make innovation happen faster. But I can tell you, would never have happened if we relied only on government funding. Too slow. So we were blessed with some fantastic philanthropic support that allowed us to get started early. And of course, once you've shown you can do it, then NIH will happily give you a grant to continue doing it. And so we've also done well with grants. But all of these components have made it successful and proves that you actually can get biologists and engineers to talk to one another in very productive ways. Now, talked a little bit about some of the challenges. The answer to how do you solve it, there's only one answer: innovation, or reduce population by some awful means, but I don't even want to talk about that. Now, Bob Solow, who is an amazing economist, won the Nobel Prize for doing an analysis of economic growth after World War II. And what he showed is that 50% of that economic growth was attributable to technology, a very, very important discovery, basically underscoring that slide I showed you with William Gladstone saying, what's it good for? And Faraday could have said, well, this is, you have to have 50% of your economic growth comes for the kind of stuff I'm doing. Well, he said, you'll tax it. Now, the United States understood that Vannevar Bush understood this. And that was his plan for the second half of the 20th century. Invest, invest, invest in fundamental research. The outcome will be economic growth. So we kind of got it. And this is such an interesting curve. The red line here shows federally funded research from the 1950s to almost today. The numbers always lag in pulling them in the analysis. So this is federally funded research, and you'll see that it picked up in the early 50s, coincident with the Apollo project, right? Peaked in the mid-1960s at around 2% of GDP, and has been falling almost steadily since then. Today we're at 0.7, 0.8% of GDP. Still a lot of money. And why do I reflect this in terms of percent of GDP? Because it reflects our nation's commitment to building technology, our national ambition in terms of what kind of technology position do we want the country to have. Now, some of this slowdown in federal funding has been picked up by business funding. Industry has invested a lot in, I would say, research, but it's R&D, research and development, and the business side is much more development than fundamental research. So the total, is just around 3% of GDP. But it's very important which side of this equation you're playing on. Now, after World War II, the United States played this game by ourselves. The other nations that could have competed were investing every penny they could get into rebuilding their countries. We had the advantage of not having fought the war on our territory. However, it's very different now. This shows you a comparison of other countries in the world that are competing to be technology leaders. And you can see that already today, South Korea, Japan, Germany are spending more as a fraction of their GDP on research than the United States is. And the line that always gives me kind of pause or worse is this bottom line, which is China. As I say, these analyses lag. You've got to be out a couple years before you get an accurate report. And so whether it is this week or next month or next year, China will surpass the United States in the amount of investments they're putting into R&D. And some people say, that's okay. New technologies will emerge someplace, and indeed they will. But I feel very strongly that the United States benefits so much from this kind of enterprise, we should be committing to it at a greater level. So what do we need to do to promote convergence? Not just all research, but convergence. First of all, we need sustained federal funding. For those of you who have any experience with federal grants, some years it goes up, some years it goes down. It's very hard to plan your experiments for 5 or 10 years when you're not sure about funding. We need flexible funds for cross-agency collaborations. I described the difficulty in getting funding for this kind of stuff. Sometimes we get it together. The Human Genome Project was funded by the Department of Energy and the NIH. The National Nanotechnology Initiative, which put the United States back on the map in nanotechnology, 4 different agencies collaborated together to fund that. The Current Brain Initiative also is a cross-agency project, but we do it episodically and kind of sometimes rather than doing it in a determined way, I think we need to figure out how to do this all the time. And a very big deal for me is policies that support investments in innovation. We don't privilege people's investments in what we call tough tech. You know, there is tech that takes 18 months to go from idea to market. The kinds of technologies I'm talking about take 15 or 20 years. Capital-intensive, long-cycle industries, that's where the future is built. And I'm, you know, along with many investors think that we should be privileging investments in innovation, giving a bit more tax advantages than we do today. And this may sound odd coming from MIT, but I think we do have some distance still to go in amplifying and accelerating university industry collaboration. It has been incredibly productive for MIT and some of our colleagues, but I think even MIT should be doing it better. Now that we've got great opportunities to speed technologies from discovery to marketplace, I think we could be doing better at it. So all in, that's the story of Convergence 2.0. I am incredibly optimistic that in any number of areas, the biology parts list is going to provide technologies of the future that are almost impossible for us to even imagine today. It's going to take some determined effort, but you know, I actually, you know, love the idea of kind of, you know, reliving the Vannevar Bush dream of investing so that we can have new products, new industries, and through that build economic growth, and that we will be able to meet the needs of the almost 10 billion people who will be on the planet by 2050. And you know, I've mentioned this as I've gone along. I am a huge fan of national ambition. I'm a huge fan of shared ambition. I've seen so many places where people's individual efforts have been amplified extraordinarily by sharing an idea with others. And it will not surprise you that one of my last call to you all this evening is, boy, couldn't we use a national ambition of some kind to unite the nation in this time of great polarization? So with that, I'm happy to take your questions. And again, I thank you for having me on your campus.
So we now have some time for questions. So if you have a question, please raise your hand, and Sabrina or I will bring the mic to you. Please do stand up when you ask your question and try to keep them relatively brief. And as always, priority will go to students.
Hello, thank you very much for your talk and for coming all the way over here. I was wondering, you talk about all of these innovations coming out of the Koch Institute and essentially institutions that investigate for academic purposes. I'm wondering what the transition is for these findings, and then they go to the private industry, and then you said the end goal is, for example, to have the filter reach the market. I'm wondering what your experience has been seeing these innovations transition from purely motivated by discovery to profit.
Yeah, it's a great question, and one of the questions is, what's the time frame? And so the example I said probably too quickly, but it's a great example, is Herceptin, which is a life-saving drug for a particular variant of breast cancer. The discovery of the gene on which Herceptin is based was, you know, at least 15 years before. So it's a long way between discovery to something that's viable in the marketplace. And I don't know that there's any way to speed that up. You know, you can jump in halfway through. You've got, you know, the Herceptin gene, and you can, you know, mark your starting place differently. But, you know, to my mind, it's that original discovery. For example, Angie taking years to develop these viruses that can build batteries. She doesn't have a battery company. She has other companies because she's trying to figure out what the form factor is going to be of her battery. So it's a very, very long road, but it's such a productive road. I'm not sure that's your question, but the other question I think that was embedded in you, so people do the initial studies. As I say, Faraday was not studying electromagnetism so that we could have iPhones, just purely out of the joy of discovery. And that is an incredibly inefficient process. And the reason that federal funding is required for that is that no company can make the bets that are going to pay off in 15 or 20 years. And frankly, when you're doing fundamental research, there are more losses than wins. So it's a complicated economic story, but history proves that if we don't walk this route, we're not going to get to technologies of the future.
Hi, thank you for being here. I just had a question of, so you talked a lot about how we need innovation, but I think my question is more fundamental in the sense that how do you push more students to get into core science? Like I am applying to grad schools right now, but I'm one of the very few of my all of cohort who's applying to grad school. Same for bigger schools. Mm-hmm. A lot of more people want to go to medicine than they want to go to core fundamental research. So how do you solve that problem? I understand that money is a problem, like your stipend compared to a biotech job is nowhere near, it's like a $50,000 difference. Right. So how do you motivate like students like me or just like science people to not go into applied research, especially in this post-2008 era where everybody has this mind where do engineering, do medicine, just have a job which is stable, which makes you money?
Yeah, so that's a really terrific and tough question. So this kind of pursuit is not for everyone. You got to be a little, let's just say, unusual. Devote your life to fundamental research. And many people have asked me today in various venues of, how I made my choices and, what do I recommend? I mean, the thing for me is I just loved it. I couldn't not do science once I had discovered it. And so it's not for everyone. However, one of the, I think, totally reasonable disincentives is this rocky funding environment. So if you're doing some research either as an undergraduate or post-graduating from college, and you like the work, you love the work, you think it's important, and your principal investigator, your PI, can't get funding for it, you think, why would I do that? It's just too hard. And so I think that part of the funding problem, and I remember having this conversation with the then NASA administrator who was at MIT and visiting me in my president's office, and I said, you can't have the bottom fall out of NASA funding for 2 years or 3 years. He said, oh, it'll come back. I said, it doesn't make any difference. When it comes back, the students will all be gone. And so this is very much investing in the long term, and you have to have a view of your nation's, your institution's future over the next 25 or 50 years. It's not for today or tomorrow because you've got to close the budget. It's making decisions that will determine the direction of the nation decades from now. So that's one of the reasons, probably the most important reason I'm so passionate about sustained funding. It's important for the research project, but it's desperately important for students who have that little quirky character that makes you want to do research, and at some point you realize just too hard. That's one answer. The second answer, and I have to say I rely on communities like this. So there are many things that any of us might be unhappy about in our nation today, but one of the things I worry about most is the acceptance of a view of the human condition as only as Homo economicus, meaning that your value is determined only by how much money you have, not by how you've benefited your community, not how you've contributed to the world, not how you've taught students. I mean, there are any number of roles that people take, not because they get top dollar for it, but because they love it and they're committed to others. And so the thing that worries me most about this nation today is how that viewpoint is receding. And we need champions. And for those of you who are blessed to be on this campus or other campuses like it, our faculty are the saints. They are the people who decide to spend their lives in the academy with little financial reward, but enormous personal reward, not just in the research themselves, but in bringing forward the next generation of our country. So I'm fighting it, and there are others who are fighting it, but let's just say it's among the things I'm not optimistic about is this current trend that drives so many people who would be delighted to be doing other things towards something that is not so delighting, but makes them a lot of money. And I can tell you, I'm old enough now to have met a lot of people who have followed the Homo economicus model, and when they get to be about my age, not so sustaining. So I think this is an issue that each of you is going to have to solve on your own. And I understand, I also have friends who have made lots of money or just enormously happy, and that's great. But you've got to figure out what is going to be most soul satisfying to you.
We have one at the back here.
Thank you. Hi, first of all, thank you. I'm really curious about those virus batteries you were talking about. I was wondering if you could briefly go into a little more detail about how it's possible to like redesign a battery in a way that doesn't use lithium or cobalt and has like a significantly less like environmental impact.
Right. So it starts with our ability to manipulate viruses, and this comes out of molecular biology. So a lot of the tools that we use today were parts of the discovery of molecular biology back in the 1950s and 60s. So viruses were the experimental organism, but now we know how to use them as tools. So it starts out by persuading a virus to bind whatever it is you want that is not an epithelial cell. And Angie Belcher, others are doing this. Oh, I should also say, these are only a few examples. There are dozens of examples in every one of the domains I describe. I just choose these because they appeal to me. I know the people, and so they have their interesting stories to tell. So viruses evolve. So when you put them in under conditions that they're not used to, some die, some live, and they live because they have mutated their nucleic acid to adapt to that new environment. And so when Angie puts her M13 into an environment with lithium, some viruses bind to it, some don't. The ones that don't, she washes away. The ones that do bind, she takes and will test them again on another round, and develops strains of viruses that bind these components. Now, an anode is not that complicated. What's great about batteries, they're very simple. Volta described them, 225 years ago. They're layers. It's cathode and anode, alternating a stack of various metals with some electrolyte in between. So once you understand that all these viruses are serving as a scaffolding to hold the components that you need to hold in place, that's the basic idea of the virus-made batteries. The viruses are not alive, right? So the age of living machines is a little bit of a sleight of hand. They're not living. They're made from living things that are now dead. Because the way the components of the batteries are organized is simply by the structure of the viruses, it does not require the kind of temperatures that are required to organize these metals if you have to melt them and get them to reform into the form factor that you need for the batteries. It's just what shall we say, it's just a scaffold. Does that help? You're welcome. Yes. Hi.
Thank you so much for coming. As I understand it, venture capital investments are really important in reviving, for instance, the semiconductor industry in the US. But as you were saying, some of the more biomedical developments take hundreds of days to even multiple decades to come to fruition. So my question is, with venture capital firms that are ever more worried about turning profit now, and not to mention just the use of an item, but also the scalability and the safety of an item, they have no way of predicting that. I guess I would just ask, do you have any ideas about how to change the institutional priorities to harness the power of venture capital to fund more of these types of innovations?
Yeah, so that's a really good question. So the question is, how do you fund something? This is the question for tough tech. How do you get investments that will basically stay with the technology long enough or sequence the technology? Most of the startup companies that I know go from one cycle to another cycle of funding, bring new funders in. For biologics, not so hard. Of course, I live in the epicenter of biotech, biopharma, and the VCs that support that. And I think the thing I would ask of my VC colleagues is that they open their aperture in terms of what kinds of individuals and what kinds of products they're willing to consider at the outset. Sometimes many universities have venture funds of their own to kind of bridge the gap. I'm not sure I'm crazy about that model, because what the VCs bring to the party is not just dollars, but also expertise. There's a huge amount to making a successful company beyond getting the technology to work. And I would say right now in terms of biologic products, I just had a press piece come out today about the paucity of women in biotech, biopharma, which is amazing since we've been graduating more women than men in the biological sciences for decades. But again, opening the aperture to a larger set of ideas. They've got a lot of money on the line. They're taking a lot of gambles, and you can understand why they're a little bit resistant. On the technology side, I didn't talk about agriculture, but the water and the battery side, it's a little tougher because their startup world is not so frothy, shall we say, as bio world. However, so this is one of the reasons I'm a little concerned about the United States' ability to compete. Aquaporin AS, it's a Danish company. And when I was visiting them, I said, are you not worried? I mean, this is going to take a long time to get these filters to the stage where they're going to be making anyone any money. And Peter Holm Jensen said, I don't worry about it so much. I've got very, very long-term investors. So the country of Denmark is committed to having a startup economy on tough tech. The Carlsberg Foundation, very, very long-term funding, and also Singapore. So other countries have understood the importance of long-term, and it's not just VCs, who are, racing to, to make the profit. So there are other models, and I think, obviously, venture capitalists and investors generally don't care what country you're in, and so tapping into those, shall we say, longer perspective funders is going to be an important piece of making this work.
We have one over here.
Hi, thank you for coming and talking today. So I wanted to ask, the FDA and other government entities pose a lot of obstacles and sometimes stifle innovation. So how do you think we should regulate this when thinking about bioethics? And should we prioritize expediency of innovation or safety?
Wow, great question, and complicated, really complicated. So I'm a big fan of the FDA because I want to be able to rely on the medicines I take, right? And the food I eat. The FDA is not infallible. So the FDA has undergone recently a number of innovations under Scott Gottlieb and Peggy Hamburg, and have really tuned up their processes to be almost up to date. One of the strategies that many of these companies use is to bring the FDA in early. So rather than waiting until the end where they actually have a product, bringing members of the FDA in to help them develop the technologies. We had a project at MIT on continuous manufacturing for pharmaceuticals. Old-fashioned way of processing is batch processing, which is kind of the way you do it in the lab, where you start out in this flask, and then you move stuff to this flask, this batch, and then you move it over here. And that is not particularly efficient. And most manufacturing has gone to continuous methods where it's just moving along all the time. And one of the challenges for using continuous manufacturing for pharmaceuticals, FDA didn't know about it. And so the project at MIT on continuous manufacturing brought the FDA in at the very beginning so that the processes that were developed and the new chemistry that was developed would be, they'd be approving it as you go along. So that's another way to just bring the FDA in a little earlier. I think safety is a very big problem, and one of the interesting dilemmas right now is not necessarily the rapidity of FDA approval, but what we are seeing in a number of drugs is what happens after that. The biomanufacturing technology and the security meaning the health security of manufacturing in other countries and how closely we can control that. So that's actually where I worry more right now, than I'm worried about the FDA slowing things down.
Hello, thanks for your talk. I was hoping you could talk a little bit about how the evolving field of neuroscience, as a neuroscientist, could potentially play in this convergence 2.0, and then if you've came across any studies or new technologies that could tackle some of these social problems that you originally addressed.
Wait, I'm sorry, you say that again, because I've only heard, I think, 2/3 of the words.
Sorry, okay, I'll go
Yeah.
again. Thanks for your talk.
Thank you.
As a neuroscientist,
Okay, that's fine, thank you. No, yeah. No, I do want to hear the
as
question.
a neuroscientist, I was hoping you could talk a little bit about how the evolving field of neuroscience could potentially play in this convergence 2.0, and then if you've came across any studies or technologies that could tackle some of these systemic social issues that you originally addressed.
Yeah, so yeah, I have to say, so when I look at the development of different parts of biology, neuroscience is still quite young, but there is a chapter in the book about bionics. And so it's a very clear example of convergence for smart prosthetics. So if you need a prosthetic leg, right now the legs don't communicate with your brain, and so you can't feel the ground under you, and it's not responsive in a way that your natural leg would be. And so I talk about some new prosthetics and new amputation techniques that give a prosthetic limb some of the sensitivity that your natural leg would have, and that comes out of Hugh Herr's lab. And then I also talk about the technologies that have developed, amazing technologies. Oh, I'm sorry, I forgot to mention something, and thank you for reminding me. It is not that I am dismissing computation. Computation is going to continue to move at an accelerating pace, and frankly is going to be part of all of these technologies that I've described, but I figure other people are dealing with that world just fine. So the other technology I talk about is ways of helping people who are paralyzed, quadriplegic from injury or stroke or disease, and rather than have them basically locked into a body that does very little for them, how to gather from electrodes that are implanted in their brains their intention. These are people who can't speak, so they can't say, oh, I'd like to have a cup of coffee. It's just, they're in a terrible situation. They are essentially living dead. So these are technologies that allow their intention to be recorded through an array of electrodes that sit in their, in this case, the motor cortex. It allows them simply by thinking to drive a robotic arm, or in some cases, their own arm, which is animated with electrodes, to allow them to engage with the world in ways they haven't since their injury. Really astonishing, and I would say that is just the beginning of it. There's a tremendous amount of work in deep brain stimulation that is now in what I consider to be the realm of science fiction, but actually working. So people with, many people with Parkinson's disease have been helped by having stimulating electrodes put in a part of the brain that is affected by Parkinson's disease, and their tremor is alleviated almost instantly when the stimulator is turned on. They're also using these kinds of stimulators to control epilepsy. And here's an incredibly way out there idea, not yet in practice. But what's key to all of these brain stimulation, brain recording technologies is there are two states. There's the state you want and the state you don't want, right? So if for epilepsy, you don't want the epileptic state, you want the normal state. And what these stimulators do is record from the brain, and they can see the pattern of neuronal activity, and when it starts going off into the epileptic pattern, there's a stimulant, an input signal that, in the best of cases, stops the epileptic signal from progressing. Amazing. So one of the people who's worked on this, a neurologist named Lee Hockberg, described to me kind of his dream, which is there are other episodic neurologic problems like schizophrenia. People with schizophrenia have normal periods, and then they have schizophrenic periods. And if you could detect again what the difference is in brain activity and find the right place to stimulate, there's a possibility that you might be able to revert these people back to more normal periods than schizophrenic periods. So, for me, I find this very exciting because the brain is so complicated, and the idea of finding the gene, the synapse, the nerve cell that you need to attack for these terribly devastating diseases, I think is much worse than looking for a needle in a haystack, let's just say. And instead, using a systems approach, I think offers a lot of possibility. And so probably because the world of neurology and psychiatry has been not entirely refractory, but really very hard to provide therapies. I think there's a lot of potential in this new way of thinking about the brain, a new way of thinking about engaging biologic with engineering technologies to really change the game for some of these diseases.
Time we have for questions this evening, so please join me in thanking Dr.
Thank you, everybody.